Okay, we're now going to invest quite a lot of energy in working out how to find an inverse matrix. And rather than just jumping in and showing you how to do it, I'm going to show you why it's something which is useful to do. So the first thing is that we're going to be able to use this to solve a system of linear equations. So if we have three equations with three unknowns, so that's the first one, and then 4x plus y minus 3z equals negative 3, and negative 2x minus 5y plus 3z equals negative 3. So I have three equations and three unknowns. I can write that as a matrix equation. So that's exactly the same as saying a matrix made up of the coefficients. So 3, negative 2, 1, 4, 1, negative 3, negative 2, negative 5, 3, multiplied by the column vector x, y, z equals 2, negative 3, negative 3. Okay, because if you multiply these two things, so first row into the column, you get 3x minus 2y plus z equals 2, which is just the first equation. So the three rows give you each of the three equations. So we can take a set of linear equations and write them as a matrix equation. Now if I write the general form of that, in general it's the same as saying that A lots of x, y, z equals some column vector. Okay, that's the general thing. Now if I can somehow magically find a matrix, I'll call it A inverse, and multiply both sides by A inverse, so that nothing's changed. And if A and A inverse cancel each other out, so these guys cancel each other out, I now know that x, y, z is equal to this thing. So I can find values for x, y, and z once I evaluate this. So the trick is being able to find a matrix that when I multiply it by my matrix of coefficients, gives me effectively 1. Gives me the identity matrix. So the key thing is that A inverse times A has to equal the identity matrix. So if I can do this, if I can find A inverse for A, then I can very quickly find out what x, y, and z is. So let me show you how I mean. So if I'm dealing with A as being this matrix up here, so 3, negative 2, 1, 4, 1, negative 3, negative 2, negative 5, 3, then A inverse equals negative 1 over 42, lots of negative 12, 1, 5, negative 6, 11, 13, negative 18, 19, 11. Okay, at the moment, that is magic. Okay, you have no idea at all how I did that, and that's what I'm going to show you over the next half dozen videos, is how we turn a matrix into its inverse. But what I'm saying to you is that this inverse should be really, really useful, because now I should be able to use this to solve the system of equations. So looking at this equation here, I'm trying to tell you that x, y, z should equal A inverse, negative 1 over 42, negative 12, 1, 5, negative 6, 11, 13, negative 18, 19, 11. Lots of the constant matrix, which is 2, negative 3, negative 3, which is negative 1 over 42. Okay, now to the multiplication. Negative 24 minus 3 is negative 27, minus 12 is negative 42. Negative 12 minus 33 is negative 45, minus another 39 is negative 84. And then we're going to get negative 36 minus 57 minus another 33 is negative 126. And if we multiply just scalar multiplication, the 42's into that gives us 1, 2, 3. So x equals 1, y equals 2, and z equals 3. Okay, and those will be the solutions to the set of simultaneous equations that I started with. So if we can work out the inverse matrix, then it's relatively easy to use that to work out the values for x, y, and z, and hence solve system of simultaneous equations. So the next half a dozen videos are going to go through a process which culminates in being able to do this step here, being able to turn a matrix into an inverse matrix. And surprisingly, you'll see that it's not magic at all, it's just basic mathematics.